Yes, it's time to start our session. My name is Stanislaw Czapp. I am from Gdańsk University of Technology from Poland. I am the chairman of this session, session Electrical Engineering. I would like to welcome everyone to our session. We have 5 presentations, and I see that we have 19 minutes per presentation, including short discussion. Yes. First presentation is entitled Extraction of Cardiac Cell Membrane Fractional Order Capacitance from Current Response to Voltage Step, and presenter is David Kubanek from Czech Republic. Is David Kubanek connected to the system?
Yes, I am here. Yes. Can you hear me?
Are you ready to present? Okay. You can share your screen, your presentation, please do it.
Okay, I will try it to share the screen and run the presentation.
Oh, yes, yes.
Do you have a full screen
yes,
view
yes.
of my presentation?
Yes, I see this presentation. Other participants?
Yes, we see.
I hope yes. Okay, okay. Please start your presentation. I think around 15 minutes because we should have a few minutes
okay.
For short discussion. Okay.
Okay, so thank you, Mr. Chairman. Good afternoon. My name is David Kubanek. I am from Brno University of Technology. And I would like to present you our paper called Extraction of Cardiac Cell Membrane Fractional Order Capacitance from Current Response to Voltage Step. Me and Jaroslav Koton are from Brno University of Technology, and Olga Svecova, our colleague, is from Masaryk University in Brno, from medical faculty. Can you hear? Can you see my pointer? Can I show like this cursor only?
Yes, yeah, I see arrow.
Yeah, the arrow. Yeah, so it's okay.
Yes, yes,
I can point by the arrow. So short introduction. Maybe you heard sometimes about fractional order elements or fractors that are passive circuit element for realization of analog circuits that realize differentiation or integration of non-integer order between cross voltage and through current. These fractional order elements are something between resistors or capacitors. You can see here the admittance relation. It looks like this. It's Laplace variable S to the power of alpha multiplied by F, by constant F. It's something similar to capacitance. And here is the main difference, that the power of S is alpha, and for classic capacitor, it's of course, it has value 1, but in this case, we consider alpha between 0 and 1. So if we choose it 0, we get a classic resistor, and if it is 1, we get capacitor, but if it is in between 0 and 1, it is fractional order element, and in particular, in this case, we consider fractional order capacitor. This passive element has application in various control systems, in filters, generators, and particularly for modeling of electrical properties. For example, some biological materials or real-world systems or real-world materials. Classically, the biological materials are modeled by this circuit. it consists of 2 resistors and 1 classic capacitor. But if we replace this classic capacitor by fractional order capacitor with this form of impedance, yeah, I showed it already here, but this is reciprocal value of impedance, we can get better modeling of, for example, biological materials. And this paper tries to optimize this modeling exactly by implementing fractional order capacitor into this model, where originally this element was classic capacitor. So let's see how the modeling of biological materials, in this case, cell membrane of cardiac cells, how it will look like, whether the accuracy will be increased. The main task was to get the parameters of the circuit model. These parameters are this resistance, and alpha and F parameters of this fractional order capacitor. For obtaining these parameters, we use numerical methods that minimize the least squares error between analytical response of this circuit model and the experimental data that are measured in frequency or in time domain. In our case, we will have current response in time domain with voltage exciting signal. So, as I told you, in standard cases, the standard capacitor is used for modeling the electrical properties of the cardiac cell membrane. But in this paper, we tried for the first time to employ fractional order capacitor to model the electrical properties of the cardiac cell membrane. So this is the objective, and we will see how large we get this parameter alpha, because this is the measure of fractality, or the difference between classic capacitor and the fractional order capacitor. This is the experimental measuring setup. Here we can see in orange color the measured cardiac cell. The technique is called patch clamp technique, and it measures the membrane current responses to changes in membrane voltage. So the voltage is applied by this electrode to the measured cell, and here the cell membrane comprises this substitute circuit. And as I told you, this capacitor is normally standard, but we will model it by fractional order capacitor. And here we have second electrode, and the current flows in this blue way. The cardiac cell was extracted of Wistar rats. It is laboratory rat that is frequently used for these experiments. The imposed voltage has this waveform. It is a normal rectangular pulse, and the recorded current, the current response to this imposed voltage looks like this. In ideal case, it is the form of this dashed line, but due to real properties of the measurement setup, it has this full line form. And from the time Ts, we can measure, or we can detect the properties of the electrical model. So this is the response this is the current response to the imposed voltage of the cell membrane. Here we have analytical description. It means relations for current response of the circuit model with fractional order capacitor. In the paper, you can see more detailed derivation of this formula. Maybe here I can see only that this E symbol means Mittag-Leffler function. It is a special function, something like generalization of exponential function known from classic capacitor. You know that classic capacitor in RC circuit charges according to exponential, but fractional order capacitor charges based on this time-dependent Mittag-Leffler function. And this is, as I mentioned, the standard capacitor exponential current waveform. So we tried to detect both fractional order capacitor and standard capacitor in the circuit model of the cell membrane. For detecting the values, it means the resistances, fractance, and alpha value, we used minimizing the error of this mathematical relation against the recorded current response. It is written here. This is the recorded measured current, and this is the relation for expected current or computed current from this mathematical relation. We tried to minimize this error by numerical methods in MATLAB. So here the black line shows the current response that was measured versus time by the measurement setup of the cell membrane. You can see that the time scale is logarithmic. It's because we need to show better the low values, but actually these low values of time are not so important. We will approximate the waveform from this sample. It is the initial time TS, because here we have some transient parasitic response or parasitic beginning of the measurement that is not valid, but from this time we can approximate the measured line by the model with fractional order capacitor. It is the red line. I will tell you about it on next slides. And other lines that are results of fittings with various elements and various methods. So in this slide, just look at the black line. That is the transient response of the recorded current to the voltage step. The amplitude of the voltage step was 5 millivolts. So now, as I promised, look at the red line. This is the response of the Cole model with fractional order capacitor that provides the best fit with the recorded black current. Yeah, here the traces overlap, but you can see some differences between the lines. And in the next slide, I will show you errors of the color lines from the black one. And it will be seen that the fitted line with fractional order capacitor provides the lowest error. The green one is fitted with classic capacitor. I have told you already that we have also tried to minimize the error with classic capacitor. And the blue line is a so-called 3P method. It is a method that fits the model to the measurement data by extracting only 3 points, 3 time samples on the black characteristic and computes classic capacitance of the cell membrane. So let's look at the errors. These are the relative errors of fitted responses. So here we have current relative error in percent, and here again we have time in seconds. Beginning in the time TS, we see that the red line has lowest error, and it is the fitted response with fractional order capacitor. If we fit only with classic capacitor, we get a higher error, approximately plus minus 7%. Here at the red line, it was only plus minus 2% approximately. And the last 3P method provided even higher error of about 12%. So it is the least accurate method. So as you can see, using fractional order capacitor in the coal circuit model can provide the lowest error of modeling the cell membrane capacitance or cell membrane electrical properties. This table that is also present in the paper summarizes the extracted parameter values of the circuit model and errors that were seen in the previous graph for the particular considered extraction methods. You can see that the fractional order capacitor in the model that was used in this work provides the lowest error, about 2.6% maximum. And also the least square error is the lowest from all these three methods. And the detected parameter alpha, that is the order of the fractional order capacitor, is approximately 0.9. So it differs from the value 1, that is typical for classic capacitor. It differs only about 10%, but still this difference in alpha provides very good improvement in modeling of electrical properties of cardiac cell membrane. To conclude, we have described method for determining parameters of cell membrane circuit model with fractional order capacitor that is based on current transient response when applying voltage pulse. It was proved that the coal model containing fractional order capacitor is able to better describe or approximate the recorded current response in comparison with the corresponding models with classic capacitor. In our case, the extracted value of fractional order was approximately 0.93, and the maximum relative approximation error of the current response is reduced approximately 3 times when using a fractional order capacitor instead of classic capacitor in the substitution circuit model. Thank you for your attention.
Thank you very much for your clear presentation. We have 2 minutes for discussion, a very short discussion. Any questions? I can see. So I have one question. Could you say some words about experimental validation, verification? Is it possible?
Yes, I am actually not the person or author that dealt with these experiments. Maybe for more details, you can contact Olga Svecova. If you leave me email, for sure I am correspondence author, so you can write me and I will give you contact for Olga Svecova, who is making these experiments. but it's done at the medical faculty of Masaryk University in Brno, and they measure these separated cardiac cells of laboratory rats, and they try to investigate exactly the capacitance of the cell membrane. So they input there the current, the voltage impulses, and sense the current, and also compute the models of compute the parameters of the circuit models. Maybe you can look at the paper. I think there are some lines in text describing this measurement methods. So there is, I think there is, it is described there in good detail.
Okay, thank you very much.
Mm-hmm.
Okay.
Thank you.
Hello, I have a question. Thank you.
Yes, please. Question from Palanga.
Greetings to Palanga.
So
yes, please.
Okay.
The presentation was very interesting. Never thought of cell membrane circuits in this way. But I'm curious about the capacitance value that you have used in your circuit. Can you please more elaborate on what kind of capacitance do you suggest in such circuits, and why?
Yeah, do you mean how to realize this fractional order capacitance, how to get it in circuit?
Yes.
Yes, it's also very big science. I also deal with it a little bit. Maybe I can. We don't have time, but this this fractional order capacitor can be realized by series or parallel connection of classic resistances and classic capacitances, classic capacitors. And if you connect them in a proper way, you get approximation circuit that behaves like fractional order capacitor. Yeah. It is also mathematical approximation. You get something between resistor and capacitor. In this case, it is closer to capacitor, and that's why you use there such a ladder connection, series and parallel combinations of resistances and capacitances to get this value of alpha between 0 and 1.
Thank you.
Mm-hmm. You're welcome.
More questions? Oh, yes, we have to finish discussion. Thank you very much again, and we have to go to the next presentation.
Mm-hmm.
Next,
I will stop sharing my screen.
Stop sharing, yes.
Where is it? I'm sorry. I was looking the bottom of the screen, yeah.
It should be.
But I have only option to share screen, not stop share screen. Maybe I will leave this room and it will be okay. Okay, so thank you.
And connect, please connect again.
Connect again.
Okay, thank you very much. Next presentation is entitled Battery Package Fused Boost Bar Design for Cylindrical Battery Cells, and team from Croatia, presenter Antun, Premec, Croatia. Please start your presentation. I can see presenter from next presenter, Antun Premec from Croatia. Is Antun Premec connected to the Zoom platform? If not, then we have to skip to the third presentation. Team from Poland. Lithium-iron-phosphate battery performance controlled by of an active BMS based on the battery to cell method. Presenter Wojciech Kurpiel. Is Wojciech Kurpiel connected? I saw Professor Miedzinski, but I...
Yes, I am. I'm connected.
Yes, yes. Ah, yes, okay, okay. Please share your screen. Oh, yes.
One moment.
Yes, yes, yes. Okay, yes. Your presentation is visible, so you can start to present.
Okay, thank you very much. Okay, welcome everybody. My presentation is about lithium iron phosphate battery performance controlled by an active BMS based on the battery to cell method. Well, electric drives are being used more and more in mines. This requires a careful selection of the source of electricity. The source of electricity should be safe at work, especially on environment and dangerous with fire or explosion. The development of technology makes it possible to use batteries from the lithium group. They are more expensive than lead acid batteries, but have better electrical properties. However, they must be properly managed and protected to be successfully used in noxious mining environment. The main problem is to prevent damage to the lithium batteries used. Such a situation may lead to the ignition of a damaged cell and its explosion. Therefore, it's imperative to use lithium batteries strictly within the safe voltage, current, and temperature range specified by the producer. In order for the lithium batteries to last as long and as safely as possible, they are connected to electronic supervision modules labeled battery management system. The task of the BMS system is therefore to control the cell parameters online and in the event of exceeding their limits value, alarming or disconnecting the battery. A very important function of the BMS system is balancing the energy of cells used to increase the efficiency of the battery and its life. The need for balancing results from difference in the load routing capacity and or resistance of individual battery cells. These differences are due to manufacturing tolerances and operating conditions of the same links and tend to increase during operation. As the capacity value change over time, weaker cells that are overloaded during charging. This can damage the battery because if at last one cell is mismatched and shows a small capacity, the capacity of the complete battery is limited. The research shows that there is a real chance for the safe and effective use of lithium-iron-phosphate batteries commonly used in vehicles to power various mining devices and drives. This requires the use of an active BMS system in order to increase durability, safety, and high operational reliability in mining conditions. Therefore, taking into account the expectation of mines, it was decided to use a lithium battery for a PCI-1 overhead mining vehicle. Its general views is shown in the figures on the picture. That is comes to BMS solution. The literature pays attention to two practical methods of balancing cells in a battery, active and passive. The third method of selecting cells with very similar electrochemical parameters is firstly very expensive, and secondly, maintaining constant parameters of the cells during operation is very difficult. The most commonly used in practice is passive balancing. It consists in dissipating the excess energy of a given cell into heat through the resistors used. It's not good because it only starts to activate after disconnecting the battery from work and starting charging. An alternative to passive balancing is active balancing. This can be done in several ways. However, they are all based on the transfer and distribution of energy between the cells. This reduces energy losses related to the dissipation of excess energy into heat, creating optimal operating conditions for the cells. As a result, their service life is extended. Due to the lack of active BMS available on the market, especially for specific applications, the authors developed and tested two different solutions of this system for powering PCI-1 overhead vehicles. In general, active BMS solutions are quite complex and their price increases with the number of cells. Therefore, in order to reduce the cost of preliminary considerations, the tests were limited to batteries consisting of a maximum of 8 series connected cells. Block diagrams of battery measurement system with connected BMS system with active balancing. The left, the cell to battery method was used here. This is the transfer takes place from the most charged cells to the entire battery pack. However, in the case of the second active BMS solution, the battery to cells method was used. This method uses energy transfer from the entire battery to the weakest cell. As a result, the change of individual cells is equalized. The tests were carried out for headway lithium-iron-phosphate cells. Due to the need to control the temperature of each cell during BMS operation, it was necessary to determine the location of the measuring point with the high test temperature. The test results indicate that the high test temperature occurs at the positive pole of the cell, which is shown in the diagram. After the completion of the temperature test, further tests were carried out for the 8 cells batteries. These have been linked to a suitable active or passive BMS for comparison. First of all, the efficiency was tested at room temperature, about 20 Celsius, with free heat transfer from the battery to the environment. To test the effectiveness of BMS balancing on asymmetric loading of the cells was needed. Therefore, for the unloaded battery, randomly selected cells from 1 to 3 were discharged in the system. Both the voltage and temperature of the battery and individual cells were controlled. Each test was started with a fully charged battery. The loading continued until the voltage of any of the cells reached the minimum value started by producer. The test carried out have shown that both the voltage values of the same cells and their temperature may differ from each other even when loaded with the same current value. For the selected free battery cells operating without a BMS system, this is clearly visible in the diagram. Therefore, an active BMS system should be used. To compare the performance of the developed active BMS system, the technical parameters have been appropriately adjusted so that the balancing is activated then when the voltage of any of the cells drop below 95% of the rated value. You can see that the cell temperature is uneven and it gradually increases with the battery life. However, its value does not differ much from each other without and with BMS at room temperature for free heat transfer. The conducted research shown that the use of any of the two developed active BMS system extends the battery voltage decay time on a single charge compared to operation without BMS or with passive BMS. Therefore, the battery life is longer. However, it was found that an active BMS system using the battery to cell method gives much better results. Extending battery life on a single charge can be significant, and many times the decay times compared to working without a BMS and or with a passive BMS. For the case of the tested number of loaded cells, it was found that it was not less than 100% when the relative number of unevenly loaded cells was not greater than 50%. Ensuring long-term, reliable, and safe operation of lithium Lithium-Iron-Phosphate cell requires above all online control of their parameters during operation. This applies, of course, to both temperature and voltage. The conducted tests showed that individual cells of the same type show different change in temperature and voltage fading, even then loaded with the same current value. Therefore, it's necessary to balance them during operation. Therefore, the lithium-iron-phosphate cells recommended by the authors can be employed to power selected suspended mining vehicles, provided the use of right active BMS. The solutions offered on the market, mainly passive BMS, are not recommended for mining applications. This is due to the undesirable heat dissipation over the equalizing resistors. Therefore, the equalizing current values must be limited. It contributes in unfavorable extensions of balancing times and, as a result, significantly reduces the efficiency of the powered electrical devices. The research carried out have indicated the greatest usefulness of the active BMS solution for cooperation with lithium-iron-phosphate batteries powering the selected suspended mining vehicle. The voltage fading for a single charge increases by at last 100% and depends on the number of unevenly loaded cells. This effect is non-linear and is the greatest for the number of cells not exceeding 25% of the total number of cells in the battery. It should also be noted that in a case in ambient temperatures significantly reduce the voltage fading, it does not affect significantly the cells overheating. Thank you for your listening.
Thank you very much for your presentation. Any questions to presenter? Yes or not? No. No.
Yeah. Hello.
Yes, Professor Miedzinski. Yes, please.
Yeah. Oh, sorry. Okay.
Yes, Professor Miedzinski, please turn on the microphone. Professor Miedzinski, do you want to say something, because the microphone was turned off?
Okay, and now it's okay. Can you hear me?
Yes. Now it's okay. Yes.
Okay.
Yes.
Okay, thank you. I'm so sorry. This, Mr. Chairman, dzień dobry, panie profesorze. I was not able to attend this conference due to many different reasons. Just not a question. I would like to only add some comments why we use the active BMS system, since in many cases we have a passive management system which is widely used in mobiles, in vehicles, in, for example, buses and everywhere. Since our goal was to apply this cell to the mining vehicle operating in a hazardous environment, it means the hazard of methane and coal. Therefore, even that this BMS system is much more expensive with this passive one, but without using this BMS active, it's impossible to employ safely these cells. So as you know, these cells are widely used in any cases, for example, in our PC computers, in mobile phone and everywhere, provided that temperature is not overheated. We found out that what is very important things that these cells are indicated by relatively high thermal inertia. What does it mean? That even that our loading current and our discharge current is not higher than this recommended and this allowed by the producer, but even it lasts for lost time. Therefore, this cell is not able to be cooled. Therefore, it's increase of temperature and it rise evidently to the explosion. Therefore, that's very, 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 very interesting. And then that improve our efforts to employ such equipment for this purpose. Thank you very much.
Thank you for this comment. I see that I know that if it is for a mining application, it should be also spark-free performance. Spark-free.
Yes, that's right.
Not only temperature, high temperature is dangerous, and also spark-free performance.
That's right.
Okay. And questions? Any more questions?
Yeah, one
Yes.
question.
Yes, please.
Yeah,
Question from Olga.
Yeah.
Yes.
I'm Audrius Baranauskas from Litgrid, representing Lithuanian TSO. My question is concerning the cells in the pack. As I understood, you propose the active battery management system who can balance the cells state of charge in the one pack or rack. Yeah.
Yeah.
Would it be possible to have or your proposed battery management system could be applied for different packs with a different state of charge balancing? I mean that, for example, one pack could be dedicated for one reasons and another packs could be dedicated for other reasons in the whole system. So would it be possible to have such different applications while taking into account your proposed battery management system?
Okay, that's a very good and very interesting questions. Yeah, look, he has forgotten to say, underline that the experiment was tested on the battery, which capacity was 10 times smaller than we really used. And finally, we performed our experiment was much higher battery packed. At the beginning for the experiments would use the battery of capacity 10 ampere hours. However, for the application, it was 10 times higher. It was 100. Therefore, the very important was to this purpose, what you said, you are right, we can use it. However, we can select carefully the current under which we can charge the cells under operation. Charge can be for balancing, so-called not charge, so-called balancing current must be carefully selected. That's a very important thing.
As I understood, your proposed method can be applied for that.
Yeah.
Okay, thank you.
Thank you very much for this question and response. Any more questions? No. Okay, we can finish this presentation and discussion. Thank you very much again. And please stop sharing your screen. Your screen is still visible. Oh, yes. Okay. Thank you very much. I have a question referring to the previous presentation. Team from Croatia. Is Antun Premec connected to the system? No. Okay. So let's go to the next presentation. Presentation number 4: comparison of performance of PVDF-based piezoelectric energy harvester with commercial piezo sensor. Chandana Ravikumar from Lithuania. Okay, please share your screen. Ah, yes, you are in Palanga, I see. Okay.
Excuse me.
Yes, Antonio.
I'm Antonio Persic. I'm here instead of Antun Premec.
Okay, your presentation will be after this presentation, okay?
Okay, not a problem.
Okay. Yes. Okay. Please start your presentation.
Here at KTU, my paper is about the comparison of performance of PVDF-based energy harvesting device with commercial piezo sensors. So I'll begin with the introduction, motivation, and what are the challenges that we aim to overcome, and the harvester system that is proposed, along with the working principle and structure is suggested, and setup of the experimental investigation, followed by results and comparison with other works and recommendation for future research. So the object of this work is a multi-layer piezoelectric vibrational energy harvesting device consisting of a flexible cantilever beam covered with PVDF layers. So this PVDF film is used to convert the vibration to electrical energy, and it utilizes the high D31 capacity of uniaxially oriented films, and the bending or the lengthwise extension of the structure helps to generate the small amounts of electrical charge that can be used and stored for other low power electronic devices to function. So the typical applications could be to benefit sensors and measurement instruments that are used to gather real-time data and traditional power sources where it's impossible to apply the traditional sources in case of batteries and cables, in asphalt and on the road platforms where we have vibrational energy at the most. And the best application scenario is in ultra low power wireless sensors or IoT devices. And advantages would be piezoelectric energy has high energy density compared to electromagnetic induction or electrostatic techniques, and it has easy scaling to micro and nano scale compared to the other techniques. So, and it's also flexible when it comes to PZT material. Other than PZT material, of course, in PVDF material, it's very easy to be incorporated in wearable electronic devices. And coming to the challenges, because we have unstable application environment, usually with vibrations, it has different resonant frequencies in the environment where we try to employ these harvesters. So it makes it difficult to have accurate estimations for selecting the suitable harvester resonant frequency. So each harvester has a different frequency range, and it becomes hard to select a particular harvester. So that's the reason why we need to have multiple resonant frequency harvesters that can vibrate at different frequency ranges and has a broader area of application. And another problem is the impedance mismatch, where we lose most of the harvested energy up to more than 50%. So we need to have a better optimized power management system. That is where we use DC-DC converters and supercapacitors that can be charged from the voltage level provided by the DC-DC converters. And the device size is also a very important aspect when it comes to energy harvesting, because the form factor and the board thickness, the dielectric material, all such factors have a lot of impact. And the cost, of course, nowadays, with the boom in energy harvesting industry, the cost is gradually relatively going lower. But before it was definitely much more higher compared to the traditional cables and battery systems. But now also, because of the maintenance of batteries becoming very expensive, up to 200 euros for every change of battery in different hard places. It could be underwater, or it could be on the asphalt on the roads. So it becomes really hard to change the batteries now and then. So that is where we have a energy harvesting system playing the role, because we don't need regular replacement of batteries, but once a lifetime investment, which could be which could work until like 3-4 years. That's our estimation after thermal cycling of our product. So now we see the proposed harvester system where we have the vibration source, and then the energy harvester is placed on or inside the application, which is the source of the machine that's vibrating. So there it's the AC vibration, AC voltage is converted to DC rectified output, which is then connected to the DC-DC capacitor, DC-DC converter, and then a supercapacitor, and then to the sensor. Now we see the experiment setup where we have to place the harvester on the exciter, as we see in the photo. The cantilever is placed on the shaker, which is connected to the amplifier and power supply and signal generator. It's excited through these sources. We can, for our experiment purpose, we have used sinusoidal wave excitations, and the working principle is like this, where we have to use a tip mass. Usually steel tip mass is fixed to the cantilever, loose end, and the base of the cantilever is a steel core on top of which PVDF layers are glued using epoxy resin. Once as the tip mass is varied, the vibration frequency varies and the amplitude also varies. So we have to make a optimized harvester, which takes a lot of experimental investigation. Here, as we see, different sizes of cantilevers were made to find out what approximate length and width of the cantilever needs to be used for the highest level of voltage produced. As we see, 23 by 64 millimeters were the optimum dimensions of length and width of the harvester. And the other figure that we see is sensors from MIAS, measurement specialties, commercial sensors, PVDF sensors. And we have tried to compare our harvester with 4 such sensors connected in parallel. And this is how the frequency response of our harvester and the piezo sensor looks like for different excitation values, 0.2, 1G and 3G excitation values. So we see up to 5 times higher voltage, RMS voltage of our harvester, which means about 10,000 times more power density, because the volume of PVDF used in our harvester is very much less compared to the PVDF used in the sensors by MIAS. So when we compare the results, as we see with other works also, our harvester is way much optimized and much more in terms of the power produced, because it's about 9.26 microwatt per millimeter cube by G. So which means it's at par with PCT ceramic sensors also. And this is a short video of how the harvester can be employed in a real-time scenario. I think it should work. So it's just a short video, because after this, we actually show how much of voltage is also seen in the multimeter, but it's not really visible here. So I'll just tell you what the values are, because up to 495 macro watts of volts of power we could observe in our harvester for a volume of 54 millimeter cube. Which is comparable to the best performing PVDF-based energy harvesters within the same volume reported so far. And despite the low power, low piezoelectric coupling seen in PVDF, it still has up to 5 times higher power because of the proposed harvester design configuration. And this is also because of the bimorph nature of the PVDF layers that we have used and the optimized design of the steel plate supporting higher amplitude of cantilever. And this is mostly also because of the longer width to length ratio that we have employed in our harvester. So these are some references that I compared with my work, and thank you.
Thank you very much for your presentation. Are there any questions directly from Palanga or maybe from other parts of the world? If not, I have one question. Could you say some words about the parameters of the supercapacitor? Maybe I missed something. Could you say something about parameters of the supercapacitor? But I saw that in the system on the block diagram you presented rectifier and then supercapacitor. Could you say something about the parameters, capacity and other parameters?
I don't know much about the supercapacitor because my work is mostly to optimize the voltage until it reaches the supercapacitor just with the rectifier output. I can say up to 14 volts RMS voltage is what we have at the moment that goes to the supercapacitor, but it doesn't charge entirely because of the voltage level mismatch. I think up to 1 volt is what we see in the supercapacitor for now, but our aim is to reach up to 3 volts to have more applications with our harvester. But for now, we are still under the borderline.
Okay, thank you. Any more questions? Okay, thank you very much again for your clear presentation, and we can go to the presentation number 2. Team from Croatia, battery package fused bus bar design for cylindrical battery cells. Presenter Antun Premec. I know that we have other presenter. Other presenter is connected. Yes, Mr. Antonio. Yes, please share your screen.
Okay, just a second. Can you see the screen?
Yes. I can see it. Yes, please start your presentation.
Good day, ladies and gentlemen. My name is Antonio Persic, and I work as a researcher at the Department of Electrical Machines, Drives and Automation of the Faculty of Electrical Engineering and Computing of the University of Zagreb. I will be talking about our latest paper, the battery package fused bus bar design for cylindrical battery cells. My colleagues and I are working on a project for a company called Novatec. We have a goal to design a battery package for a brand new electric minibus. I will present our findings in these following steps with some introduction, the experimental environment, fused bus bars. We have 3 experiments and some simulation results and the conclusion. Well, with electric vehicles becoming more popular in recent years, battery pack safety is more important than ever. Cylindrical battery cells are often used because of its higher specific energy and because of its ease of battery pack distribution within the vehicle itself. It's well known that the case of a short circuit due to a faulty safety mechanism or mechanical damage, the battery cell can start the process of a thermal runaway. Although cylindrical battery cells have the pressure valve as a safety mechanism, it is not without fail. adding another component in the battery pack design might add cost and slightly worsen the characteristics of the battery pack. But the added layer of safety might be worth it. For this purpose, battery cell fuse tabs are introduced as an additional safety measure. One of the challenges of developing a battery pack is achieving a battery pack tab is achieving robust electrical connection between the battery cells. The battery cell tabs must be robust, they must handle high currents if needed, and can dissipate heat very effectively, and can be used to achieve effective welds to the battery cell. So they need to be able to connect the cells with minimum voltage drops. Aluminum and copper are the two most popular materials that are used to produce electrical connectors. Another alternative, which is basically a do-it-yourself variant, which is most commonly used, is nickel. We wanted to test it, and we wanted to see if we can accept the material to our battery pack. Nickel's connection is achieved with spot welding, which is very cheap and widely available, whereas copper connection is achieved with ultrasonic or laser welding, which is a little bit rare here in Croatia and a bit more costly. Well, the equipment that we used to conduct the experiments were the AC/DC bidirectional power supply, a PC for data acquisition, thermal camera, and an Arduino development board, along with the temperature sensor that communicates to it via one-wire protocol. Well, the experiments are conducted on 3 samples. The top figure presents the nickel tab developed to connect 16 21700 battery cells with fuse cutouts. It is intended to connect them in parallel for this project. The thickness of the nickel and copper tabs are 0.2 millimeters with their fuse width of 1.4 millimeters. The third sample is made out of a nickel roll, which is bought from eBay. The fuse tabs, the thickness is 1.15 millimeters and the fuse width is 1 millimeter. There are 3 experiments conducted on the aforementioned bus sheet material. The first experiment is to determine the lowest value of the electric current needed to burn the bus bar's fuse, where the current was gradually incremented to its cutoff value. The second experiment is to determine the voltage losses due to the temperature rise of the bus materials, where the current is set at a specific point. The third experiment, well, basically the cutoff currents from experiment 1 were applied to their respective sample tabs, and the fuse cutoff time is measured to see how fast the system reacts to an overcurrent state. To determine the lowest current value needed to cut off the tab's fuse, the current is incrementally increased every 15 seconds until the cutoff point. In these following slides, in the following 3 slides, the T0 and T1 temperatures represent the temperature sensor values, where T0 is placed 1 centimeter from the fuse, that's on the positive terminal, and the T1 is at the negative terminal. On this figure, we can see the nickel tab from a few slides before, and they break at a current level of 27 amps. The second one is the copper tab. It breaks at a current level of 41 amp, and the thin nickel sample breaks at a current level of 9.8 amp. The second experiment results. So basically, the experiment is conducted at different current levels. for a period of 60 seconds, or if the sample reaches 90 degrees Celsius. Why? Because we know that if we have a battery package, we want to keep it from 20 to 45, ultimately 50 degrees. We want to keep it in the sweet spot so we don't so it doesn't degrade. The samples have to undertake current levels that are derivatives of the battery cell C rate factor. So basically, we have a 21700 battery cell. We know its current capabilities, and that's our starting point. Well, on these, the results are here as we thought they would be. The nickel tab reaches 90 degrees Celsius at 7.37 amps, the copper tab at 17.15, and the thin nickel tab at 4.9 amps. The power losses and the percentage voltage losses for the nickel tab, along with the calculated internal resistance, can be seen in the table in front of you. Well, these figures on the following two slides represent the power losses due to Joule heating in each sample at the same level of current. Well, because the AC/DC power supply was connected basically into a short circuit, and we limited the current. So any watts that we could have measured, it was basically heat generation. The losses comparison were done at a low electrical current set point to include all the sample tabs. As it can be seen from the losses comparison figures in front of you, the thin nickel tab has the highest internal resistance losses. This was expected. This is due to the nickel's comparability, high resistivity, and the tab's smaller thickness compared to the other two sample tabs. The nickel measurement ended after 22 seconds because the sample reached 90 degrees Celsius. So basically, that was our interlock. You can see that in this picture. This figure. This is the green line. So basically, when we got to 90 degrees, we just stopped. The following figure contains the 3 tab variations in the third experiment to see how fast the fuse can break and disconnect the circuits. So this is experiment number 3. The nickel sheet has a high internal resistance and cuts off in just a few seconds at 27 amps. The reading on the temperature sensor is lagging a little bit in these figures compared to the moment in which the fuse has cut off. Well, this is due to some lags in the sensory and the measurement. But if we check the voltage, we can clearly see where's the breaking point. The copper fuse is cut off at 15 seconds at 41.65 amps. And the nickel sheet has a high the nickel sheet at 9.8 amps. The nickel samples show a lower increase in temperature due to low heat conductivity. The simulations that we made were done in a COMSOL environment. It was conducted in a Joule heating module, which enables the calculation of a temperature rise and distribution along with voltage losses generated in the fuse tab 3D model. The samples are set in an environment of 20 degrees Celsius, and basically that's the starting point of all measurements. The figure you can see in front of you represents the COMSOL measurement environment and the temperature distribution along the model. The points with the highest temperature are expected to melt. Those are basically those dark red points. This is the simulation result for copper. We see that the current is 41.65 amps. Basically, it took 22 seconds to reach the steady state. And at that steady state, the maximum temperature was 758 degrees Celsius and the minimum 327 degrees Celsius. The maximum voltage loss here was 0.28 volts. For the thin nickel, we had it on 9.8 amps. The time was 22 seconds until we reached the steady state with 990 degrees Celsius, and basically we had a 0.79 voltage drop. The current of the thick nickel was at 27 amps. The breaking time was 7 seconds. Well, the steady state temperature should be around 1544 degrees Celsius, where the minimum temperature was 990.7. The max voltage loss was 2.1 volt. Now, keep in consideration that basically the rated voltage of the battery cell is 3.6 volts. So basically, we can have problems if the voltage loss is too big. For instance, in this instance. Well, to conclude, the overall conclusion is what we expected, that the copper is a superior material which can be optimized for higher electrical currents and lower temperatures in comparison to nickel. Having said that, copper's mechanical properties make it more challenging to properly connect to the tab of the battery cell. The power loss percentage is much more significant at a higher electrical current level. So from a power efficiency point, it is advised that the fuses on the bus bar should be a bit over-dimensioned. When we're talking about fused tab cells, the heat generation is quite large. It's better to use wire bonding in that matter. So basically, when we connected everything to the battery pack, we found that, for instance, the nickel just created more heat, and the battery cells were heating just because of the fuses. When we talk about wire bonding, basically we take one small fraction of a wire, we ultrasonically weld it from a battery cell to the tab, and it breaks as quick as a normal fuse. Thank you for listening. And do you have any questions?
Yes, thank you very much. Are there any questions from the audience? I cannot see questions. No questions. Yes, we have only 13 minutes left. No questions? No. Okay, thank you very much for your presentation, and then we can go to the next presentation. So please start your sharing your screen. Thank you. Thank you very much. And now we have last presentation, last but not least, real-time investigation of temperature effect on the induction motor equivalent circuit measurement change. Team from Turkey, presenter Hakan Terzoglu.
Yes, hello.
Yes. Yes,
hello,
it's
dear
connected.
participants.
Yes. Okay, please share your screen.
Okay.
Again, is yes. Yes, I see your presentation, but as you know, theoretically we have only 2 minutes, so try to compress your presentation. Yes. Please turn switch on your microphone.
Okay, do you hear me?
Yes, yes. So we have theoretically 2 minutes, so try to compress your presentation, yes?
Oh, thank you. Sorry, this problem. Hello, dear participants. I am Hakan Terzioğlu, a doctor from Selçuk University Faculty of Technology, Department of Electronic Engineering. I will talk about real-time investigation of temperature effect on induction motor equivalent circuit parameter change. According to the global energy assessment by the International Energy Agency, electric motor driven systems are responsible for 53% of the electricity used worldwide. In the electric motor driven system sector, 77% of the electrical energy consumption is used by mid-size motors with power values below 375 kilowatts. 80% of the medium-size motors used are induction motors. The large-scale use of induction motors makes them ideal candidates for energy efficiency improvement. As a result of the research and development studies of the factories where induction motors are produced, general parameter information under constant running temperature and load is given as fabrication data. However, in the industrial field, motors must be used in a wide variety of laws and regulations. Therefore, temperature change in the stator winding of the motors created by these variable operation condition cause the motor parameter to change instantly. Change in the motor parameter cause the motor not to be driven correctly and the energy efficiency to be low. Equivalent circuit model is used to determine the parameter. In addition, since the values of each phase are equal in three-phase motors, it is sufficient to determine the parameter by applying equation substitute on single phase. It is also common to use simplified equivalent shape, L-shape circuit for parameter estimation. The effect of the amplification factor in the flux state observer loop made relative to the L-shape equivalent circuit can be considered for an induction motor equipment with a circle cage rotor. The calculation of the moment by the state observer is based on estimating the stator flux in a fixed coordinate system. The result of the study reveals that modern AC electric drive system require developed high accuracy system in speed control without installing rotor position sensors. As a result, it is necessary to calculate the parameter of various various laws and factors correctly in order to examine the dynamic performance of induction motor and to derive their mathematical models. In recent years, the importance of the subject has emerged and the studies on the determination of electrical equation substitute parameters of induction motors have increased. In the studies, method consisting of artificial intelligence techniques are widely used to determine the equivalent circuit parameters, which is a nonlinear and multivariate problem. Some of these methods can be listed as a genetic algorithm, differential evaluation algorithm, particle swap optimization algorithm, etc. When the studies on electrical equivalent parameters estimation of induction motors, which vary with the effect of environmental factors, are evaluated in the literature, it seems that it is not possible to use measurement or equivalent circuit-based methods in the engine at the design stage. On the other hand, analytical or finite element method based at the design stage, based method can be used in the design phase. However, it cannot be applied to a pre-manufactured engine because the exact geometry and material data may not always be fully available. An offline parameter estimation can be made using the particle swarm optimization technique. However, this cannot predict online the effect of environmental factors such as temperature and load over time. Estimation made with only the thermal equivalent parameter are limited and insufficient. In fact, electrical parameter can be approximated using a multi-objective genetic algorithm. However, this method involves a complex equivalent circuit modeling. As a result, it has concluded that the nonlinear and variable parameter of induction motors can only be determined accurately by the experiment in which multivariate effects are observed together at different motor powers. In this study, we have done in the article environmental conditions that have an effect on the parameters were applied to the engines and on the same experiment. In addition, by including the motor power variables in the experimental content, the effect of the power difference on the rate of change in the parameters is shown. Thus, our study differs from scientific studies done so far in terms of analyzing so many variables together that have an effect on the parameters. The result of the study, which we obtained by analyzing many environmental effects at the same time, are thought to provide a universal modeling in future study with data mining. When the result of the change in the equation circuit parameter to the environmental factors of the induction motor, whose foundation was laid with this study, are combined with our future studies. It is thought that it will bring a new perspective compared to the studies done so far, but both in the derived methods of the induction motor and early failure detection. Design of the test. In this study, we aim to determine the variation of induction motor electrical magnitude and electrical equation circuit parameters with motor winding temperature. In addition, by interpreting the test data obtained for this purpose, it is requested to compare the general test models with the parameter results. The block diagram of the system test created for the real-time analysis of the variation of parameter with temperature is given figure. In the block diagram in figure, two different power motors of 0.75 and 1.5 kilowatt are used as induction motors. The dynamo was used to carry out the loaded running test of induction motors. The technical specification of the induction motors and dynamo used in the test are given table 1. An example view of the screen page pointing this data is shown in figure. The driver was used to read the current voltage, power factor, power, and torque data of the motors in this investigation. In addition, all parameters measured and calculated in the system are solved in the memory of the PLC XSL format, and this file can be accessed by the computer. An example experimental setup is shown in figure. For example, parameter measured by the driver and parameter calculated by the PLC, input parameter and calculated parameter. Yes, an example experimental setup is shown in figure. Result from the test. The tests were applied to engines of different power, no load, loaded, and at different shaft speed. At the beginning of the test, the value on the motor nameplate and motor stator winding resistance were entered into the SCADA system. Output parameter values were calculated according to the input parameters measured during the test. If the formulas used in the parameter calculation are briefly mentioned, if measuring the stator resistance of a star-connected induction motor with an ohmmeter, or measuring the stator resistance of a delta-connected induction motor with ohmmeter, stator resistance and stator resistance change with temperature, RSE formulation. Induction motor slip and torque formula from the approximate equivalent circuit formula RMXM. The variation of each test input and output parameter with temperature was tested to visualize the data in a more understandable way. It is graphical variations, figure 6, are given in the graph in the figure 6. In the graph, in the figure, the letter Y is seen next to same parameter. These parametric symbols are used instead of the approximate equivalent circuit parameter. For example, it is symbolized as R2Y instead of R2 exponent. The change of all the other data will be analyzed in the form of a data table. When the graphics are examined, the no-load test parameter of both 0.75 and 1.5 kilowatt motor showed more oscillation than the loaded test parameters. These oscillations decrease when the motor are loaded. This is due to the oscillation in the current. The graph in the picture are driven by averaging the values read in real time according to the determined sampling time. The blue line on the graph shows the parameter change per second, while the black line on the graph shows the average of the parameter oscillation values. Since it is important to determine the electrical parameter correctly in induction motors, the input parameter were calculated with traditional formulas according to the system output parameter obtained in the tests. Thus, it was possible to compare both the input parameter received from the system and the calculated input parameters. The compatibility of the system and software installed as a result of the comparison has been verified. The recalculation of the output parameter according to the input parameters obtained from the test setup is given in table 2. When the error rates in table 2 are examined, it is seen that system data are consistent. As it is shown, parameter determination of induction motors can be done by general tests. The 3 tests used for this are the DC test of the induction motor, the idle test, and the short circuit tests. Since the main purpose of our study is to change the parameter according to the stator winding temperature, values were taken to the start end and temperature of these general tests. The input parameter obtained from these tests are shown in table 3. During the operation of the motor, oscillation occur in the current. Since it's accurate and written in the table, it is expressed as the current symbol, I average. Yes. We cannot obtain this stator winding temperature change during a motor runtime in a parameter determination with general test methods. Therefore, in the general test method, idle and locked rotor test, the parameter values at the motor stator winding temperature at the stator of the test and the motor stator winding temperature at the end of the determined test period were determined. The determined
Excuse me,
parameter.
dear presenter, try to go to conclusion because we have 13 minutes after the full time, yes?
Okay. Okay. I quickly. Do you hear me?
Yes, I see your presentation and I hear you.
Okay. I continue. Okay. The effect of the motor stator winding temperature of the parameter calculated from the general test and the parameters obtained from the system test was plotted graphically. When the graph are examined, the variation of the both experimental parameter with temperature show parallelism figure. Show graph of the these rates of change. It was mentioned. It was mentioned that the parameter change during the motor runtime will not only depend on the stator winding temperature. It is known that besides the temperature effect, it is factored in the motor shaft speed and load. In figure, the effects of 0.75 and 1.5 kilowatt motor shaft speed and stator winding temperature on the parameter are compared in the no load and load run test. Conclusion, this statistical analysis presented in the test results section allowed us to reach the following conclusion. One, parameter of induction motor varies by about 10% according to the motor power and environmental factors. Two, the error rate mostly below 2% between the data of the proposed method and the general induction motor test data indicate the reliability of the system. The highest oscillation values in the parameter occurred in the no-load test. The motor work more stable under load and the parameter show less oscillation. 4. Parameter change curves determined by various calculation methods in all engine operation conditions are very close to each other. This article partially determined the effect of the temperature change in the induction motor windings on motor parameters to a preliminary study. In our future studies, the scope of the change in the induction motor parameter will be expanded to include different induction motor powers, different speeds and different loads, and temperature transfer losses will be analyzed. Thus, an accurate thermal model will be developed for the induction motor. While creating this model, it's aimed to present mathematical modeling by processing many data stacks showing the electrical equivalent parameters. The mathematical modeling we aim to find will not only cover the engines in the design phase, but also the engines that have been manufactured before. In addition, it is thought that universal modeling will be presented by analyzing many environmental effects at the same time. This modeling will be a mathematical modeling that is simple to use and we can get results quickly. Thus, it is thought that the mathematical modeling we obtained as a result of our research will bring a new perspective to both the driving methods of induction motors and earlier failure detection compared to the studies done so far. Right. Thanks for listening to presentation.
Thank you very much. In fact, we have no time for a discussion. Maybe only one question, if any. No questions. Okay. Thank you very much again for your presentation. I would like to thank all the presenters, the audience. and I wish you a fruitful further part of the conference. I think we can close the session. The session is closed. Thank you very much.
Thank you.